Okay, we're going to continue on here with whatever we were talking about before. I think we're in solutions. That sounds sort of familiar. All right, so I think we've been talking about the solutions chapter before break. And first off, a reminder that a solution has two parts. One is the solute, which is the smaller part of the solution. The other part is the solvent, which is the larger part of a solution. And really, both of those things together make up a solution, which is a homogeneous mixture. And it is the ones that get the aqueous symbol next to them is typically what those guys are. We talked about some different types of solutions and solubility. And the idea of like dissolves like. So things that have similar sort of intermolecular forces, the way that they interact with themselves, and if they come across something else that interacts the very same way, they tend to be very soluble in each other, which means they will mix. So typically things that are soluble in each other are things that are ionic and polar. Those guys work really well together. Things that are polar and polar also work really well together. And things that are actually nonpolar and nonpolar work well together. And that's because they're both going to be using really dispersion forces, which is their intermolecular forces, while polar are ionic and polar. We'll use some version of dipole interaction between them. You really run into trouble in terms of being insoluble when you sort of cross over there and you try to mix something that is polar and nonpolar together. They really don't mix, they just sort of separate out. We talked about also, I believe, solubility rules. And we saw a table of solubility rules, I think, last time, and we could use that solubility rules to help us decide when we put together an ionic compound, would we expect it to be soluble or insoluble? If it's insoluble, it typically would be a solid, and if it's soluble, it would be a solution based on solubility rules. So for example, everybody, in group 1 are soluble in everything. Nitrates are also soluble in everything. For example, chlorides, bromides, iodides are soluble in everything, except there are a few exceptions, and a few exceptions are silver, lead, and mercury 1. And if you happen to have any of those three with a chloride, a bromide, or an iodide, then it would be the opposite, and it would be insoluble in that case. I think what we finished up on was electrolytes, if I am not mistaken. And electrolytes are solutions that will produce ions and conduct electricity. And it's really the presence of those ions that helps it conduct electricity. So there are a strong electrolyte and a strong electrolyte will 100% break apart into ions. So if you have something that is a strong electrolyte, you will not have any of the whole units together. They will really 100% break apart. You have all ions in solution. So if you had a sodium chloride solution, in the actual solution, it would be 100% the ions that are present. So you'll have this, again, solution that basically has sodium ions and chloride ions. You will not have any of the sodium chloride units still together. There's also weak electrolytes, and weak electrolytes are a little bit different. They will kind of stay together, but will produce a few ions. So for example, hydrofluoric acid is a weak electrolyte, also a weak acid. We also could recognize a weak electrolyte by the arrows that are used in the sort of equation. It is a two-way arrow as opposed to a one-way arrow that you see with a strong electrolyte. In solution, this is mainly what you have, but you do have some of these guys. So if you were to look at this sort of solution, you would mainly see HF molecules basically floating around and a little bit of HF and F minus kind of floating around in the solution. In terms of conducting electricity, strong electrolyte will conduct electricity really well. Light bulb example, I think, is where we left off and finished up on last time. It will be very, very bright. Weak electrolyte will still be able to conduct electricity, but nowhere near a strong electrolyte. So it'll kind of, the light bulb example would go on, but it would be very, very dim. And there's also non-electrolytes that we talked about. And those guys do dissolve in water, or do dissolve, but no ions are formed. So an example is sugar, which again is made up of carbons, hydrogens, and oxygens, and it will dissolve in water, to give you sort of an aqueous sugar, if you will. But they really will not create any ions, and because of the lack of ions that are there, it will not be able to conduct electricity. Any question on this stuff? I think we talked about it last time, a long time ago. Yes. Okay, so we're going to kind of pick up from there, I think. All right. So the next thing we're going to talk about is a way that sometimes solutions concentrations are given, which are what are known as equivalents. So equivalents, if I can spit that out, there you go. Equivalents oftentimes are a way sometimes solutions are measured, especially like IV bags, for example. And an equivalent is really related to the charge. So the equivalence related to the charge of the ions that are present in the solution. It really doesn't matter if it is a positive charge or a negative charge. It is actually just the number on the charge, which is the most important thing. So for example, if we had something like, say, sulfate has really a -2 charge, but in terms of equivalence, it's actually the two parts that's important. You could come up with a conversion that for every 1 mole of sulfate, you will have basically 2 equivalents, and that's basically based off of the charge. If you had something like lithium has a +1 charge, and it's really the one part that's important. You could say in 1 mole of lithium, there is 1 equivalent. So a lot of times we'll use sort of equivalence as like a conversion factor to convert between different units of concentration. Very common units of concentration are oftentimes equivalents per liter or milli equivalents per liter. And milli is the same sort of milli conversion that we use like with liters. In 1 liter, there's 1,000 milliliters, and 1 equivalent, there would be 1,000 milli equivalents. So it kind of works the same in terms of the conversion. So to show you sort of how this would work, let's just say we had 0.25 moles per liter of sulfate. And we wanted to know what the concentration of sulfate was in the solution in both of those units. So we would actually, again, use sort of our conversion factor that we just got there from the equivalence, which is this guy. And in this case, we would take in 1 mole of sulfate, there are 2 equivalents. The moles of sulfate would cancel each other out, and we would end up with 25 times 2. 0.5 equivalents per liter of sulfate in this case. Now, if we wanted milliequivalents, we would do our last conversion here, which would be in 1 equivalent. There is 1,000 milliequivalents. The equivalents would cancel. We would times it by 1,000 basically. And we would get that there is 500 milliequivalents per liter. So it is sometimes a very common sort of unit of concentration for solutions, especially when there's a lot of ions basically floating around in the solution. Question on that there. So why don't you try one here? Let's do. All right, so what would be the equivalents per liter and milliequivalents per liter if you had a solution that contained 0.375 moles per liter of, let's do phosphate, why not? All right, so take a moment, figure out what the concentration would be in equivalents. Get it. So starting really with the phosphate, which is our ion here, this is what's going to really give us our conversion. And it is, again, just the number that's on the charge there. And 1 mole of phosphate, again, it doesn't matter if it's positive or negative. In this case, it's just the number. It would give us 3 equivalents in this case. That means that if we started with 0.375 moles of phosphate per liter, really the only thing we want to change here is the moles part. So we'll use that as a conversion factor. And 1 mole of phosphate, there are 3 equivalents. The moles of phosphate will cancel, and that would get us 0.375 times 3. Will get us something like 1.1. We'll round it to 3 equivalents per liter, which would be one of the units we were looking for. Any questions on that calculation there? Now, to convert it into milliequivalents per liter, we're just going to use this conversion here. And I'll just kind of pick it up from my box there. So in 1 equivalent, there are 1,000 milliequivalents. Once again, here, the equivalents would cancel each other out. So basically, we're just going to divide it by, or multiply it by 1,000. And again, here, I'll round like I did there, 1130 milliequivalents per liter here. So again, basically we use the formula of the charge as really a conversion factor. As we'll talk about in a second here, this is really a unit of concentration, which is known as the molarity, and we can sometimes convert it into equivalents per liter. Any questions on that there? Yeah. There's a table, and as I mentioned, doesn't matter if it's positive or negative, it is really just the number of the charge. So as you can see, that's how we get those relationships from. The next thing we're going to talk about is some different types of concentrations for solutions. And the first one is what is referred to as the mass percent. It's sometimes abbreviated, as you see there, percent mass M/M, which is the mass to mass percent. And it is the mass of the solute over the mass of the solution times 100%. The important part of this one is actually the bottom here, and that is the mass of the solution. You want to make sure that you get both parts of the solution that we've talked about, which is the solute and the solvent. And the reason you want to be really careful in these type of problems is they typically will give you that information separate from each other. So it's very common that people, when they read these problems, you'll divide by the solvent only and not actually get the entire mass of the solution. So in mass percent type problems, it's a very common thing that those two things are sort of separated in the actual problem. But you basically take the mass divided by the mass of the solution times 100%. If you had a 4.5% by mass sodium chloride solution, for example, if you're given the percentage, you can convert it into really like a conversion factor that you could use. And the simplest thing to do when you have a percentage is to assume that you have 100 of something, right? And that keeps the number basically the same. So if I did have 4.5% by mass sodium chloride solution, what that means is I would have 4.50 grams of sodium chloride in 100 grams of solution. So that is how you could kind of convert out of the percentage into a usable sort of conversion factor there. If you didn't draw your arrows so long there, try that again. Now, because it is a conversion factor, you could use it like that, or you could flip it around and use it the other way where we have 100 grams of solution up on top and 4.5 grams of sodium chloride on the bottom. So that's a very common way to sort of convert out of a percentage, and you could kind of do the problem using dimensional analysis, or you could just plug and chug into this equation and solve it as well. So they both should come out the same. Any questions on that there? All right, let's take a look at one here, I think, and see. A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. Calculate the mass percent of calcium chloride in this solution. Take a moment, see what you come up with here. Okay, let's take a look here. So we're looking for the percent mass to mass, which once again is the mass of the solute divided by the mass of the solution times 100%. In this case, the calcium chloride here is our solute. It is the smaller part of the solution. In this case, water is our solvent. So again, like I mentioned, everybody's given to you sort of separate from each other. So we do have the mass of the solute, which is the 250. The mass of the solution, once again, is both the solute, which is 250, plus our solvent in this case. And that actually gives us 52.5 grams. So if you divide it by 50, you only got the solvent. You got to make sure you get both. At that point, we got everything that we need. Our percent mass to mass would be 2.50 grams divided by 52.5 grams and times it by 100% in this case. And we will end up with, looks like 4.76% M/M, and you could put calcium chloride in this case as it. Question on that one there. By the way, I think we talked about it last time, but just a reminder that the name of the solution is always the solute. So if you have a calcium chloride solution, the calcium chloride would be the solute. If you had a sodium chloride solution, the solute would be sodium chloride. So always the name of the solution is pretty much the solute. And if it's ionic, probably 9 times out of 10, if not more, it's probably going to be water is going to be probably your solvent. Water is not always a solvent, but in a lot of cases. Any questions on that one there? All right, let's try another one here. We have a concentrated hydrochloric acid solution, contains 37.2% by mass hydrogen chloride or hydrochloric acid. What mass of hydrochloric acid is contained in 35.5 grams of a concentrated solution? Take a few moments, see what you come up with here. Okay, so in this case, we're actually given the percent mass to mass of 37.2%. We are also given the mass of the solution, which is 35.5 grams. And we are looking for the mass of the solute, which we don't know yet. Once again, I do know that this is a hydrochloric acid solution, or HCl, which means that that is the solute. So if I'm asked how much of that's there, that is how I know that I'm really solving for the solute in this particular case. Now, there's a couple different ways you could do it. You can take a more dimensional analysis approach to solve it. So if you took that approach, what you would want to do is really convert this percentage into a usable conversion factor. And that basically means that there are 37.2 grams of HCl in 100 grams of solution. Or again, you could use it the opposite way. 100 grams of solution is 37.2 grams of HCl. And again, we get that really from assuming 100 and kind of converted it into a conversion factor. In that case, because I know the mass of the solution, which is 35.5 grams of solution, I would use the conversion factor here on the left so that it would cancel out correctly. And that would give me 100 grams of solution and 37.2 grams of HCl. The grams of solution would cancel. We're going to take basically 35.5 times 37.2 divided by 100. Going to give us 13.2 grams of HCl in that solution. First off, any questions on that? Now, if you really just plugged and chugged into the percent by mass formula, which is the percent by mass equals our mass of the solute divided by the mass of the solution times 100%, you would have 37.2% equals the mass of the solute divided by our mass of the solution, which is 35.5 grams times 100%. You would multiply the 35.5 to the other side and times it by 37.2%. And that would equal your mass of your solute times 100%. You then would divide this to the other side, and you would end up with 35.5 grams times 37.2% divided by 100% equals the mass of the solute in this case. The percentages would cancel, leaves you with grams, and you end up with the exact same thing you did there because it's really the same math. You're multiplying 35 times 37 and dividing it by 100, which is the same thing you did up there. So you could do it either way. You could plug it into the equation. You could solve it more like a dimensional analysis problem and conversion factors. They both come out really the same way. Any questions on any of that there? Okay, so percent mass to mass is one sort of concentration unit for solutions. There are a couple other sort of percent concentration units that we sometimes come across. There's volume percent, there's mass volume percent, these sort of percentage type units. So let's take a look at both of those there. The volume percent, which is sometimes referred to as the volume percent V/V. That is the volume of solute divided by the volume of solution times 100%. This is like percent by volume alcohol type of deal, right? This is sort of what they're talking about. The good news with this one is, and in most cases, they will just give you the volume of the solution. It is unlike the last one. They're not necessarily broken apart. So that's kind of like milliliters over milliliters. Same idea if you had a 4.5% by volume sodium chloride solution, you could also turn that into a usable sort of conversion factor. You could say you have 4.5 milliliters of sodium chloride and 100 milliliters of solution. That's basically 4.5%. Or you could flip it around and do 100 milliliters of solution over 4.5 milliliters of sodium chloride. So much like the last one, sometimes with these percent compositions, it's sometimes easier just to kind of turn them into a conversion factor, especially if you're given the percentages. Or again, just like we saw with the last one, you can plug and chug into here. It doesn't need to be obviously the same volume units on top and bottom, and usually it's milliliters and milliliters, so everything cancels out correctly. The other sort of percent concentration is the percent mass to volume, and the percent mass to volume is pretty much what it sounds like. It's the mass of the solute divided by the volume of solution times 100%. This is kind of like density, right? Density is grams per milliliter, so same idea. It's a percent mass to volume type of deal. So that is grams divided by milliliters here. And once again, it does work the same way. If you take our same sort of example, 4.5% mass to volume sodium chloride solution, that would mean that you had 4.5 grams of sodium chloride in 100 milliliters of solution. Or again, you could flip it around. 100 milliliters of solution would contain 4.50 grams of sodium chloride in this example. So once again, like all the other sort of percent concentrations, you definitely can convert them into usable conversion factors. Or again, you could just plug and chug into the sort of formula there on the bottom. All right, so in terms of percent concentrations, we have percent mass to mass, which is basically grams divided by grams. We have percent volume to volume, which is typically volume to milliliters divided by milliliters. And we have percent mass to volume, which is grams basically divided by milliliters in this case. Let's take a look at one here. What is the mass to volume percent of Br2 in a solution that's prepared by dissolving 12 grams of Br2 in enough carbon tetrachloride to make 250 milliliters of the solution? See what you come up with. All right, so we're looking for percent mass to volume here, and that would be our mass of our solute divided by the mass of the, not the mass, the volume of the solution times 100%. In this case, our solute is the Br2. Our solvent is actually carbon tetrachloride in this case. Our solvent. So basically, we just have everything we need. We do have the solute, which is 12 grams, divided by the volume here of our solution, which is 250. And that will get us a 4.8%. And that usually would be M/V. And you would go Br2 in that case. Any question on that one here? So this is an example of where water would be, frankly, a terrible solvent in this case. Water would be a terrible solvent because Br2, is it polar or non-polar? Br2 is non-polar, right? And that means if you try to put water there as your solvent, which is polar, those two things are not going to mix. So this is a reason why water would not be a great solvent in this case. That is why carbon tetrachloride, which just quickly sketched without all the electrons, looks something like that. That is what we call a symmetrical geometry, right? Everything attached on the outside is the same. That would also be a non-polar guy. So thus a non-polar guy and a non-polar guy will mix together well to make a solution in this case, yeah? So again, remember that although water is oftentimes a solvent, especially for ionic compounds, for non-polar things, it's actually terrible solvent. You shouldn't use it. Any questions on that there? Okay. All right, let's try one more here. Calculate the grams of KCl and the grams of water in 225 grams of an 8% by mass solution of calcium chloride. So how many grams of, I can't say calcium chloride, I got it in my head, potassium chloride. how many grams of potassium chloride, and obviously how many grams of water would be needed to make this solution. Okay, let's take a look at this since we're getting towards the end here. So we're given a couple of things. We're given the percent by mass there of the solution. So the solution is 8% by mass. Calcium chloride, potassium chloride. We know that the mass of the solution here is 225 grams. And we're looking for two things. We're looking for the grams of the KCl. And since this is a KCl solution, that is our solute. So you would use that for your solute or try to figure out what that is. And we're also looking for how many grams of water. Water here would be our solvent in this case. So I'm going to take the approach, a more dimensional analysis approach. So once again, I'm going to convert this percentage into a conversion factor. And that would mean that I have 8 grams of KCl in 100 grams of solution. Or in 100 grams of solution, I have 8 grams of KCl. So since I do have the mass of the solution, I will take the mass of the solution, which is 225 grams. I'm going to use conversion factor here on the left because solution's on the bottom. And that would give me 8 grams of KCl and 100 grams of solution. Grams of solution would cancel, and that would get me 225 times 8 divided by 100. And about 18 grams of KCl in this case. That would be one of the answers. That is basically the mass of my solute in this case, right? First off, any questions on that? You could also have plugged it into the percent mass to mass formula, which is basically the same math we just did. And obviously in this case, you have the mass of the solution, and that you could solve for that, which would give you this number here. Now that I have the mass of the solute, that's helpful because I do know that the mass of the solution is equal to the mass of the solute plus the mass of the solvent. And I know the mass of the solution is 225 grams. The mass of the solute I just calculated as 18 grams. And that would be our mass of our solvent, which is our water in this case. If I subtract the 18 to the other side, that is going to give me the mass of the water, which would be, looks like 207 grams of water would be necessary. Mass of the solvent, which in this case is the water. Any questions on either of those? So the solution is basically made up of 18 grams of the KCl and about 207 grams of water all mixed together. And that gives you your 8% solution that is there. Any questions on that there? All right, we'll lay it up there for today, I think.